Very happy to see you tonight. It's basically like to greet you on behalf of AKT and ourselves, IJP, so Paul Scott here to my right and myself. The idea for tonight is basically just give you a slideshow, almost a vacation slideshow if you like, of a project that's lasted for a number of years, which has been very central, I think, to our experience at the AA, both Paul's and mine. I mean, you all know Adam Scarra-Taylor, an engineering office that has a vested interest in the academic and actually production sort of side of the curriculum of the AA. Myself, unit master here since 2002, and the designer of a project that had the good fortune of beginning almost at the same time as I started teaching in diploma. In fact, a number of people here that I could mention have been involved, former students, colleagues, friends, from all walks of life, and I just felt that in the end, since the project is now finishing, it's only fair to just basically show the school, where we're at, what happened, what's going on, and that's the meaning really of this lecture. There's no theory. We're known for rambling kind of discussions of this or that aspect. Tonight, we'd just like to, show the images and the slides. So the project basically lasted for a long time. Between the two images, it's almost 4 years to the day. It was the year of the European Championship. So we had the previous one, which Chris won, the night we interviewed for the competition. And now there's another one coming up. So you see 4 years, almost to the day, between the picture on the left and the one on the right, which you can see is almost taken from the same vantage point. You can tell the little railing here of the stair. Paul and I, on the first visit, to look at basically the site prior to the interviews, and this one taken a month ago with the students of Deep 5 when we visited Singapore. Now, of course, things didn't happen that quickly. I have a picture here of Lawrence Lur, who studied under me in Deep 5, with whom we did the competition. And it was quite funny because this picture was taken in June 2004 when Lawrence just flew out to Singapore without actually saying anything, because about a month earlier we just got a phone call saying that, look, you guys got the second prize, congratulations, blah, blah, blah. And, I was actually, very happy, but I didn't actually think, nobody thought they had actually won. And Lawrence was called out of the blue and was invited to come to that ceremony in Singapore, where he was told that, in fact, there is no winner, and all the offices that have been basically declared runner-ups are actually shortlisted and ought to interview to get the job. So I basically just called me. It was in the middle of tables, and he said, look, I think it's still going, and you guys should come to Singapore. So it was a bit of a strange time, but we called the client, who said, yeah, you can come on Monday, and this is when basically Paul and I just bought tickets on the fly and basically flew out to Singapore to interview for the job. So at that meeting, Lawrence presented the entry to Mabao Tan, who's the development minister. He's sort of number 3 in the government, who I believe handpicked the project among the 3 runner-ups. And the interview proper took place in June 2004. This is a slightly later slide of one of the meetings that I believe, Paul, you didn't attend. This was the 3rd one, but that's pretty much the format, if you like, facing the a lineup of planning officials here with our local partners, the representatives of RSP, which are a very large, basically architectural practice in Singapore, myself in the middle. The funny thing with the interview was that, so as I said, there was a short list, which in the end, in September, produced 1 winner. The result being that even though the project was retained, we never actually got a prize. And there was a substantial sort of a sum that simply never materialized because officially there was no basically winner. But anyway, you're not going to complain after you've won, whichever way. And to be honest with you, after maybe 4 years, actually, Paul, would you like to just step on the side? So you get the after 4 years, I wonder basically, how that was even possible. I mean, you see, this is a slide from the exhibition hall. This is our entry. We took every possible risk, like no renderings, relatively abstruse kind of sheets, even a little bit of mathematics, a model that was, you know, the best of the AA kind of style. It's very abstract, sort of no details, no trees, breaking every rule in the book. And somehow the nice thing about the client is that they just loved it and kept the model, wouldn't return it, and basically gave the merit award, which eventually turned into a prize-winning entry. So Paul and I flew to Singapore in June, and we took that picture just to show you where the site is. For those of you who know the area, this is the southern part of the island. This is Sentosa, here on the right, this man-made island. And then you see this area is a sort of recreational park called the Southern Ridges. So it's a big planning project for Singapore. In other words, it's not really about just doing buildings and infrastructure. It's about planning this very long area. So there is basically one site, which is ours, which is here. Another one, which is Alexandra Link, another bridge. Competition was set at the same time, plus a number of other small projects that make up, if you like, that's very, very big kind of region. So this is a close-up of these models, which are very nice. The Ministry of Equipment has them in Singapore. They're all over the place at different scales. This is our site. That's our bridge, kind of. And
to put the scale into perspective there, the bridge is actually 250 meters long. So these are fairly vast areas that we're looking at on the model. And I think the criteria initially given was the distance between the two peaks, which we were trying to connect, the 250 meters, and the allowance of support piers at around a 25 meter to 50 meter spacing. Other than that, there was very little control or constraints over where this bridge could be formed, other than the model that you see there.
Yeah. It's exactly that, if you like. The competitors were offered two sites. In other words, you were invited either to do this one or basically that one. And as Paul said, you see the one we chose, Henderson Crossing, is actually a sort of great leap forward, almost 300 meters between point A and B, over a freeway, you know, with 6 lanes, as opposed to this one, which I believe a number of people did even at the AA. It's a very nice site, which is effectively a long crawl towards that avenue here, which is called Alexandra Link, followed by a very small leap, a tiny bridge, if you like, over the freeway itself. So this was more of a landscape project than an infrastructural one, or kind of a nice integration of both. I mean, if the office had been bigger, we would have done both, but it was difficult. I think someone from the office, your office, did the other one. Was it Raymond, I believe?
They didn't win.
Okay. No. So you can see the Alexandra Link here and the Henderson Crossing. That's part of the brochure that we're given. This is the jury, by the way. This is Mrs. Coe, the Director of Planning. And you see that's what the site looks like. I think Paul and I took that picture that morning we arrived. It's a strange mix of secondary rainforest and public housing. So depending on where you actually look, you are either in the jungle or in the middle of a concrete town, and it's a quite nice mix, which, for those of you who are familiar with Singapore, is quite common. Now, this is the site, and as you can see, that picture wouldn't have been possible without the bridge proper, which you see a little bit in the foreground. That's the freeway. It's a really beautiful, very, very dynamic kind of thoroughfare, sort of crossing through that sort of chain of hills. This is where the picture was taken earlier, where Paul and I were sitting. So that picture is taken from the bridge as well. So I promised I wouldn't talk about process, but it's a little bit about that as well. The project began initially as basically as an algorithm, if you like, as a piece of text, which was an early text that I wrote in IJP, which came out in 2003. So that was the first phase, if you like, of the project. There is one text here where the actual equation we used is described purely verbally. And as you can see, somewhere between the conceptual definition and then what happens much later, this is a slide of the contractor, let's say, and somebody working with a contractor, who's actually produced stencils of indices to mark every single metal load-bearing element that's part of the surface form. So you'd think that I would have asked for that, but they actually did it themselves. In other words, they bought into this idea that the indexical theme, somehow that runs behind, this conceptual text, was fairly clearly embodied physically in the material kind of making of the bridge, and they just wanted to show that and celebrate it, so they actually printed those. I haven't seen the very final stencils, but they should be on site now. So you see there's a kind of a straight link between theory and practice. That's the text in question, in which I discussed the pillow as a kind of mathematical construct. This is the seed, the egg, if you like, from which the bridge hatched. You can't quite see it right now because this is the kind of undeformed, undifferentiated kind of structure, but it's really the type of equation which, in further manipulated, has that elementary sort of figure that we were looking for, a kind of an alternation of peaks and troughs, which Paul very early defined as a succession of arches and catenaries. I'm saying this because that kind of information is what we shared at the very beginning.
I think it's worth just saying that when we had the basic parameters of the site, we sat down and started to look at what form the bridge could take without getting into the mathematics. We began to look at what an arch should do if it was going to work efficiently, what kind of span, what kind of rise it should have, and what we could work with in terms of the terrain as well, and where the support should be. So we tried to set some basic parameters very early on in the design process, which could then be fed into this mathematics here. And if you like, it would begin to inform the design from the constraints that we were working from the site as well. We also had an idea of the kind of materials that we were looking at, how those materials were going to be formed, how the curvatures could be formed, and all of this information is incredibly important to be able to bring up front and early on in the design process, knowledge about the manufacturing and the erection of the bridge itself. And all of that helps to drive out a very real solution at these early stages.
And I don't know if you remember that particular slide. Indeed, during those very early discussions, I mean, just applying if you like, some kind of a periodic noise on that produced this. And I showed this to Paul and said, "Hey, you can't do that. This is not an arch. This is not, that won't take bending." I mean, there was a really interesting discussion that actually went around. Basically something that could be very, very easily produced. And I usually use this slide to say that, using this particular method, which is IJP's sort of trademark, you can do anything you want, including something that, looks as cool as something you could do in Rhino or Maya, by more traditional means, as it were, but which, in this case, wouldn't make the kind of structural cut. So this is what Paul and I, in the end, settled for. It's this succession of upside and downside pods, or spans as we call them, which Paul defined quite clearly as being able to obviously work with somehow longitudinal members, which would be alternatingly arches and then catenaries, right, on the flip side.
And I think the important thing at this stage was, as we were developing it, we could begin to import it into analysis software and begin to test it from a very basic point of view. But at least, again, we could begin to inform the design not only with the parameters we originally set up, but now we could start to feed in the analysis that we were doing on the bridge, and we could then tweak any of these conditions that we originally set. And because George was working very much in a digital environment and had complete control over all the coordinates that he was using, it made this transition or this discussion between the structure and the architecture very easily. Things crossed the platforms very simply in terms of drawing, analysis, and between all the different pieces of software we're using. And that's very, very important at the early stages, to get a real feedback in real time.
So in the spirit of showing basically what the process really does in reality, basically that's what the succession of arches and catenaries became, and we'll go back to this. Mathematics has really informed the whole process in a kind of a give and take way, as Paul just explained. This is the seating. That's the math of the seating, if you like, which doesn't quite look like it, but in reality it's basically these areas, and so forth. So it's the same kind of relationship between somehow the algorithm and the making. Another thing that I wanted to maybe say is that over the years I've been releasing detailed pictures of the bridge, and Paul and I have been basically also saying everywhere that it's 300 meters long, but it's probably been misperceived as being smaller as what it is. And I just wanted to show you, this is the springing point. These are the pillars that Paul mentioned, which are spaced by either 24 or 60 meters. And it's a big structure. I mean, if you look at how it spans the landscape, in reality, you can't even photograph it entirely. I mean, this would be one shot of one of the 24-meter spans. So either, through the distortion of the lens or the landscape, it's not a structure that you can capture somehow in one stroke. This is the kind of information we shared early on. Center lines of members coming straight out of the mathematical equation, with the long members highlighted in red. And this was typically the type of data that you would take and ask us to reissue with fewer points or more points. That was a little bit the kind of the fulcrum of that early dialogue, no?
Yeah, very much so. I mean, if we're working with complex or irregular forms that are coming from other pieces of software, some of the big problems we have is trying to clean those models up. Geometrically, they can often carry a lot of problems within them. When we bring them into a different analysis software, it will actually fall apart because it can't understand the same geometry as where it's come from. So this kind of cleanliness or this way of working was again very important to get into answers quickly and getting real feedback into the design. And from this we could extract, as George says, center lines to all the members we had. We could begin to check geometry. We could start to think about fabrication, and we could start to think about how the bridge could be spliced, brought to site, and erected in place. So all of these thought patterns can begin when you've got an intelligent grip on the geometry you're dealing with.
So in order to leap over that gap of 300 meters, the bridge has to bend in plan so that it's a little bit longer. It also has to obviously climb, and it climbs by about 18 meters, which would be almost a 6-7 story block. And then, of course, because it's periodic, it has to undulate. And the combination of those three movements, if you like, produces an elevation like this one. And I show this slide quite often to maybe just draw one's attention on the fact that it looks like, say, a bird's eye view, but it's actually a facade, because the kind of three motions that are sort of built into that sort of parametric modulation make the form, if you like, slide in and out of alignment. So, for instance, each one of those members here, all those lines basically are shown in true shape, like you could measure them with a ruler, while at the same time they kind of move wildly, if you like, in depth. That kind of effect is quite familiar. What it means on site, familiar to those who use parametric equations, where you can easily, let's say, mistake a plan for a section and vice versa. But what that means in reality is that you see all these points somehow vary. That detail was developed to pick up those slight differentials that have to do with that sliding in and out of space. But all these members are absolutely parallel and can be flat sheet cut and or assembled. So that was an early, if you like, benefit of that particular kind of modulation on the definition of the structure. Another problem of this sort of what I call the Stephen Hall effect, because that facade that looks like a bird's eye view is pretty much what they used to call a cabinet cavalier projection, where you just draw the elevation and draw the the volume receding in depth, except that here it's spatial as opposed to being just graphical. That effect has all sorts of problems. I mean, for instance, I show this plan taken out of the tender package, on which maybe 80% of the lines shown here cannot be measured because of these distortions. So we even added a disclaimer on the tender package, somehow making sure that you wouldn't attempt to, derive any dimensions of this particular element. In reality, what does this mean? Well, you see this is a close-up of the diagram that we just looked at. In reality, it's more like this. In other words, it's a kind of completely discontinuous element. So this is a close-up of the deck where you have seating, a backrest, and a series of flights and horizontal thresholds, all of which create a very, very discontinuous kind of condition where, for instance, a landing, a tiny landing of 4 meters by 1.5 meters needs its own equation in the scheme of things in order to be segging properly with the remainder of the form. And you see what that gives in reality. I mean, this is a landing, and that's its math, if you like, which is obviously too much math for a landing if you think of it. But you need that in order to seg things together. In reality, it will produce these elements. And you see all these discontinuities, which give this rather unsettling aspect to the deck, which we'll see in a second, somehow begin in this breakdown, which forces you to reconsider what happens every 9 meters, 1.5 meter in space, with all the kind of periodic modulation. So this is our control panel, which we used, if you like, to verify the accuracy of the calculations. Make sure that you don't, split the deck open and that you can actually clear all the heights in order to land safely a wheelchair across the bridge over 300 meters. For those of you who remember, we exhibited these calculations a little bit like decoration. Was that in 2006 as part of that student faculty show, in which we basically showed the maths. You see this is the 1.5 bay shown over there. Next to Omar Al-Mariz, one of the Deep 5 students, sort of on mathematics. So the idea was to compare a little bit the process of the teacher and that of the student. And we exhibited as well the tender package, which basically, on which, basically the project was developed that year. So just wanted to show a few things about the site. Obviously, one had to shave the mountain. That happened over periods of months. You weren't there, Paul, but there were meetings with national parks where every tree was discussed.
Sure, yeah.
It was a kind of a buy and sell situation where, if you cut a tree, you have to replant one, or you can imagine, I mean, this grows quite fast, but still, Singapore is very proud on its natural heritage, and, there was quite a few discussions. This picture is taken from the from the springing point. So you see, that's where it begins and where it ends. The pylons kind of gradually appearing. And the end works. So one of the things that gave us the worst really time, both AKT and ourselves, was the pylons. The reason is very simple, is that they were not part of the equation from our end, so we had to design them, and that opened up all sorts of basically a kind of worms, really. We spent a long time on this, which basically, I'm sure, Paul, you remember, it was that scheme.
Unlike normal building structures, bridge structures are extremely sensitive to dynamics, and like building structures, we have to deal with static loads, live loads, dead loads, but then we have to respect the dynamic performance of the bridge, and that usually is very sensitive to the materials we're using in the span, and also the support structures that we're using for the bridges as well. And given that these pylons were extremely long in the centre, they undoubtedly contributed to the lateral stiffness of the bridge in how it would perform when people traversed across it. So there was a lot of discussion about the pylons and how they contributed to that. The initial competition scheme, I don't know whether you have the initial one there, but was a more solid pylon, very different to the bridge structure itself. There was comments that it needed to be perhaps opened up a little bit more like the bridge. So we began to kind of look at this kind of form, more of a tree form. But what we're finding, whilst we could meet the static analysis, that when we got into the dynamics of the bridge, it actually became very sensitive to trying to do this kind of structure. And if we wanted to open up the pylon, then we'd have to close up the bridge a lot more. So it's very much a play-off between the two systems. In the end, through discussion, we decided it would be better to add more stiffness into the pylons and maintain the integrity in the bridge. And I think probably the next slide shows... Yeah, we also looked at possibly changing it to steel to get some more stiffness into the upper part there. So part steel, part concrete, looking at the different construction techniques of doing this. But still, we needed more of this kind of form in order to get the horizontal resistance that we needed for the bridge to respond to. So there's actually quite a lot of work done on this, and many hours spent drawing the form from different angles and working out how it could work with the bridge.
So you see, as soon as the tree-like option was abandoned, we moved towards the sort of open legs, which was rejected by the local partners. So we started sort of bringing them close together, and then looked at various sort of ways of, let's say, imprinting a relief. And you can see that from that very dendritic, expressive design, we've been moving closely and closely towards that singular pylon. Then at some point we got hold of a design that Renzo Piano did for a bridge actually in Tokyo Bay, which was very, very simple and similar, except that the proportion was actually far less desirable, I think, than this one, which became our basically our final kind of option. So something very, very simple, which I'm not unhappy with personally in the end, because it does, I mean, as Paul said, when you can't quite match the maybe the kind of elegance or the spirit of the bridge itself, then you'd better go completely different and look for something that simply doesn't compete with the definition of the form above. So the pylons, of course, come in different heights. This one is about a bit taller than I am. A stump, really, which you can see is gradually cast in situ around the springing point. Before the structure is obviously overlaid on top, and we'll talk about that in a second. The middle ones are quite tall already. They're 20 meters high on the other side, and there's 20-25 meters already on the springing end in Mount Faber. And then the tallest one is nearly 40 meters. It's very high. You can see the one that's the highest one is the one on the left, which in the end I think works quite nicely. I mean, this is the situation in March 2007. I'll talk about the bit on the floor over there, which came last. And yes, in conclusion, you see because the inflection point where the surface self-intersects is where we collect somehow the lateral forces exerted by both the catenary and the arch, somehow that very simple column sitting on top of there, sort of collecting those things and going straight to the floor was, I thought, a rather desirable kind of solution. The project really exemplifies almost 7 years of research on what it means to simply, let's say, parse equations and simply look for a one-to-one relationship between the numerical series given you by the math and the center lines of material members, such as this laser cut model by Åsa Nilsson, a Deep 5 graduate in 2004. And this is basically, Paul was going to explain the basic sort of structural diagram.
Yeah, this is a typical span within the bridge. And just to explain the sort of structural components, the main bridge deck itself has a central spine member that does most of the work in supporting the main deck. That follows the bridging plan and curves to follow the bridge as well. That's in a single curvature, basically. That's kind of mirrored also on the edge of the deck here by an edge member that simply follows the same geometry as the central spine member. And then above the central spine member, we have this arch structure that rises and drops below, either creating an arch or a catenary. Now, the main problem with the arch was that, it could support the form, but also it was susceptible to lateral buckling. All arches will try and buckle sideways when they're in compression unless they've got some kind of form of constraint. Good grief. These ribs here are actually the pieces or the members that create or form the restraint to the arch and prevent it from buckling. There was certainly no way we could connect the arch to the central spine member because, of course, it would cut the bridge off from pedestrian use. So we were using these rib members not only to create the form, the architectural form of the bridge, but also to restrain the arch itself. The impact of doing that meant that the forces that would have been taken around the arch member and thrown into this central spine here meant that this would have undergone a fair amount of twisting, and it would have become a much bigger member than it was originally intended to because of the torsion it was going through. So we ended this by putting in a very subtle secondary arch or mid-height arch here that connects these rib structures and offers another line of support that takes it back to the main pylons within the bridge. So there's a series of strands here that are getting the bridge to work and dealing with these sort of kind of torsional loads. Undoubtedly, the central spine member's doing the most work, but this is kind of assisted dynamically with the bridge in that the bridge needs to respond appropriately to the dynamics and is dampened by this form, these number of ribs and the arch that it connects to, and dampening of long span structures are absolutely crucial to make them work and also to achieve a certain amount of elegance over these kind of distances.
That's an early sort of model of the edge member, central spine, the arch, which I'm holding in my fingers, and then the mid-height member, which is there in the background. The curved rib members that Paul just mentioned, so it's a laser cut kind of trial, if you like, which in reality turns into this. So as Paul just explained, every eighth of them is actually structural or fully structural. You can see the one in the background, which is sort of a box section, and the others, the infill ones, are actually eye profiles, eye beams. That's basically what the element looks. So you can see the mid-height member that you mentioned, the box sections that link the arch with the spine through the mid-height, and then the eye beams in between. These guys were laser cut, and I did get the feeling that we could actually probably even manufacture them that way. So when it came to basically making models of the long members and the short members here, I was actually quite happy visiting the steel plant in Malaysia last year where this is being cut. And you can see in the foreground an edge member for the large span. It's kind of an assembled structure. It's from manufacture with 4 thick steel plates, all of them laser cut using a 8-meter wide bed that you can see over here on site before being welded over there. So this is the edge member, I'm sorry, the mid-height member, Paul, right? Mm-hmm. And then the arch.
That's right, the main arch at the top there.
Yeah.
And these, we'll come on to this in a minute, but basically these were done in single curvature, but the model that George was actually working up in the geometry that he had was in double curvature. So there is a certain degree of rationalization, and there comes to a point in a project when you're dealing with these kind of forms where you then have to look at how things are going to be fabricated more closely and how you can actually bring the two together.
So once the members were obviously welded, they were painted on site. The painting bit of that plant is as big as a small airport, and they were left out to dry. This is an edge member with that extra piece that holds the balustrade, to which we'll come in a second. And this was our model, our own kind of study model that we basically did about 2 years ago, which obviously in reality translates into something that obviously has different dimensions and functions in a different way.
This is some of the graphics from our analysis software. This is the kind of first pass we do at the analysis, which is just the static loads before we start worrying about the dynamics. And this is really just pulling in the strands that George had worked from the model. He could very easily extract the center lines that we needed. This was brought into the analysis software, given properties, and then we begin to investigate how the bridge is working. This is a series of diagrams that look at the main arch member. And initially, because it was following the spine member within the deck, it meant it was curved in two directions. And this particular span, which is 25 meters long, about 3.5 meters high, could only be described in double curvature, so that meant it was either a set of coordinates or a set of digital information. In the UK, we can bend steel to double curvature. It can also be done by larger fabricators in the Far East. The feedback we were getting from the fabricators at the time was that we needed to rationalize this curve into single curvature. So this one and this one that you see here, sorry, this is the two main spans that give all the coordinates to achieve that. So we started by looking at what we wanted to achieve theoretically, and then if we go on to the next one, this was then our first rationalization, which was to take the 25-meter span, break it into a single curve, and build it with 5 radii, i.e. not a continuous change in radii that the fabricator would work to, but he could actually bend 5 pure radii that you see in the top right, and he could weld it together as 5 sections. That was a rationalization. And looking at the image on the bottom, that merely took the main arch member off the theoretical line by 0.5 degree. So the error was in fact extremely small. And the deviation on this arch was about 5 millimeters from the original theoretical line. The next slide shows the larger span. In this instance, by changing to a single span arch, it threw the arch over by about 12 degrees, so we weren't purely normal to the deck. And it threw us out by about 45 millimeters from the theoretical line. Well, clearly these are very, very small movements on such large spans. So initially this rationalization to 5 curves seemed certainly viable from our point of view. The next slide then took that a stage further and said, well, if we try to do it as a single curve and as a pure curve without any change in radii, what would happen? The deviation in the angle, again, was very small. It was only 0.5 degree on the typical spans, but actually we started to move about 280 mil away from the original theoretical line. And the next slide, we begin to move away again further. So at the time we were developing the design, we concluded that we break it into 5 radii for the fabricator to work on. We then started discussions, and I think in the end it was probably broken into 3. So there needs to be this recognition in developing forms and structures like this, that when we work with double curvatures, there needs to be a recognition of what we can do to simplify that, how we can help the fabrication process. It's not to say that we shouldn't do double curvature, but we should at least know the implications of trying to rationalize these kind of forms.
So on site, obviously, these considerations are, sort of a very different in that sense. This is the endworks, which was the first element to be built. So brought in straight from Malaysia, painted, welded, and then assembled on site, starting with the landing area, which you can see here in the foreground from both ends. Where this picture I took a year ago now, so you see it's gone quite quickly. The bridge, obviously, we did not excavate that last part of the site. You see how close the ground is to the steel structure. This is what allowed us to really reach those 300 meters without having to do it at great expense. In other words, the end of the bridge is actually a sort of a platform, really, that is simply looks and feels like the rest of the deck. steel-wise towards the springing point, you see the workers basically covered entirely, basically this area. You can see the spine sitting already under that sort of a network. You can also see the dampeners that are actually, picking up some of the potential vibrations, although it's not as critical, obviously, on the end works as it is on the central span. And then moving slowly towards installing basically the edge members with the support for the balconies, then the first curved metal ribs with a bit of the arch. These were, as I said, laser cut, painted, dropped on site, gradually basically assembled one by one, with basically the workers having to make sure that it's completely level, that they're completely parallel, literally the way D5 students build kind of models almost piece by piece, except that each one of them weighs 120 kilos, and unlike what this slide is showing, sometimes you're hovering 20, 40 meters above basically earth level. So it was quite an involved building site. You can see the first of the upside waves being assembled. It's even done in 3 parts. In other words, it was broken into 3 parts because there was no crane that could be hoisted up there. So they had to simply do it in 3 pieces. And that's a completed element. You see it's been welded 3 times in these areas. This is the first complete upside wave about a year ago, in which you can see all the members we discussed. It's a really nice moment because obviously it's got this skeletal feel, which will be soon lost when the timber will cover it. Also the color, which had been a kind of a huge argument amongst ourselves and our local associates, in the end turned out to be quite nice. This sort of puffy color, which has this bone-like color that I think evokes the skeletal, almost prehistoric, slightly sort of animal-like quality of the form. So continuing towards the standing point, reaching the first pylon away from the platform with, you can see an edge member that spans over this little piece of basically path. So in other words, the bridge goes over a path. There's a kind of loop kind of configuration that you see on the master plan. And reaching the first downside wave, which is still being arranged here over the first pylon. So you can see everything looks quite messy prior to the alignment. So when I visited, I went there with my ruler, worked on this beam, and then sat down, took a couple of measurements. The contractors were just completely silent, wondering whether something might have been done wrong, which obviously wouldn't be the case. But it took a lot of time to actually get a sort of smoothness behind this sort of array. So that's another view of the downside wave, again being assembled on site. You can see the difference between the boxed and the I-beam sections. On the drawings, I thought this was anathema. In other words, I was completely against using I-beams. I tried to impose flanges as narrow as possible. This was also good for budgetary reasons, but as you can see in the end, it was a bad decision because the only thing that you really see is those surfaces that are normal to the light and therefore basically look brighter. So if the flange had been, let's say, wide as the box, would have had a perfectly sort of homogeneous view that would have been pretty much close to the model, except that unlike the model, it is much cheaper because the I-beams are fabricated. I'm sorry, the I-beams are just welded together, whereas these are made of 4 separate pieces. So these small nuances, the difference between a box section and an I-beam, can make or break a project in budgetary reasons. And there were many months of discussions in 2005 over whether this or that solution would enable us to actually clear the budget, save the project, and so on and all that. From there on, obviously, the structure continued. There was no problem. It went basically all the way to being completed. What has always been an issue is the middle span. So you can see here we're right above the freeway, and the middle span, which is 60 meters high, was treated completely separately. In other words, it was not it was prefabricated in Malaysia, but the components were not actually assembled in the plant and then ferried over to Singapore. It was actually done right here on that makeshift platform in position. You can see that it's placed in such a way that it slopes already at the right angle because it was simply too heavy. In other words, you couldn't somehow wheel it or ferry it all the way on site. So it was built almost on site, right below, next to the taller pylons, for months on this kind of makeshift platform. It was even clad with timber. And then, in the space of a night, all that formwork, which you can see over here, which is quite nice, prior to the cladding, which is about to happen, all this was jacked up along this pylon in the space of a night. So you can see this is the sort of naked expression of the structure. This is a span that Paul just described, which was post-rationalized by AKT into 5 points. You can see that it's actually it looks very flattish because it's stretched mathematically to the double the height of the other waves, which it has to, so that this arch can actually span 60 meters. And then the steel guys did an amazing job of somehow converting all these lines of intersection between doubly curved areas, such as this, and flat areas such as that, build those lines in order to make basically the timber work absolutely possible and precise. I must say I'm really impressed with the steel. I think those guys did an unbelievable job, which in some ways enabled then the timber guys to work very precisely. Another thing that you notice is the scale of this. I mean, look at this guy. This is 6 meters. You can have a small 2-story building sort of hovering in there. It's absolutely big, and you can see the hoisting of the structure took place through those 2 pistons. So it was not even craned. It's too heavy to be craned. It was just hoisted up, again in the space of a night, during which the freeway had to be closed. This is it on site. So you can see that now it's been mounted and partly covered. These are the areas that I was just discussing, and you see the scale of this particular element. Anything else you wanted to say about the structure, Paul?
Well, I think at this point, for a structural engineer, this is probably one of the most interesting points in any project, where you get to see the skeletal form before any of the finishes or cladding or whatever the skins may be. But this is also a very crucial point, because it's not until you start applying the finishes that you actually know the geometry's worked, and you've got control over the geometry. There is a certain amount of tolerance to be given in fabricating curved sections. Things will never follow it exactly as it should, and I think the bending tolerance on the arches was about plus or minus 30 millimeters. It might not sound a lot on a large span, but these kind of errors can build up quite dramatically when you start to attach a timber form to it. So a very interesting point in the project, but one that I think no one quite relaxes until they start seeing the finishes applied.
Yeah. The local, basically the firm that took over the engineering at sort of tender time made a few small changes, such as you can see the tapering of the load-bearing curved ribs, which would have never allowed if it was done at a schematic design level time. But even somehow, I think in the end it doesn't work too badly. I mean, in the Rhino or AutoCAD model, this looks like a bird cage and is an absolute no-no. But by daylight, again, the kind of secondary rhythm of those members, I think, works quite nicely. So, I mean, that's called experience, I guess. There's a lot of things that just look terrible in drawing and work very, very well in reality. The only real design bit of this project is the deck. In other words, everything else is pure structure, which is also a question of design, but not in the kind of ordinary sense applied to this word. So the timber deck has been something that we thought very hard from competition time. We always envisioned it as a kind of basically a surface, obviously, a pliant one, something that we could actually bend at will, and one that would interact with the primary geometry of the structure that we just presented. In this early model, the idea was to somehow come in and out of the pod, through the thinnest of curved ribbed members. This idea was abandoned since we ended up stopping, if you like, the cladding along the spine proper. But that rest basically remained unchanged. This is an early model done by the timber contractor, showing the material of choice, the hardwood, yellow balau. One of the misleading things about this model, which he designed and sent us for the 2006 show, is that it looks, like garden furniture. It's just really flat and kind of boring. Lots of people lost interest in the project after that show. At the moment, I have it in the office, where you see where it actually, sometimes I sleep on it. But the nice thing about it is that it actually shows you what 2% of that surface is actually doing, which is the seating. Somehow, the seating area, which is indeed horizontal, as opposed to the deck, which you can see right there, which is slanting, even on this tiny sort of sliver, and the backrest, which is doubly curved, and of course is nothing like what this early mock-up shows, although of course it's a fantastic thing to have done, if you like, early on, which really showed the commitment of the timber contractor, who's really the person behind the success of the design bit of the project. So in reality, things are mostly likely single curvature, such as this mock-up for the timber balustrade, and very often double curvature as well for this detail of the corner of the pod. So you can see that every bit is actually tapered by hand. This is pretty much what the equation also is giving you, in the sense that those lines have to remain parallel, and obviously parallel to each other. You can see that if you projected somehow, if you move the light, the shadow of this element would actually be completely aligned with this joint. And if you keep that rule going, then you'd basically have to taper the elements, which they did by hand, which is quite an amazing kind of prototype. When we did this in MathCAD and then in AutoCAD, I was told that this is AutoCAD, you can't build that. And then when I visited the workshop of Venture, it was just that. It was there. I mean, it was possible. It was done. I was obviously quite overjoyed. In reality, what this means is that you clad, so the timber is gradually carpeting the end works. This is the landing. I'll show you the detail of this later. So it's very nice sort of stepping, obviously, through the discontinuities that I mentioned earlier. And this is basically what it looks like in the end works. There's also furniture that I haven't captured on the picture, which follows a little bit this idea. So you can see the way, basically, the cladding has now simply covered these end works. But how is that really done? Well, it was pre-cut. We made all the drawings. We developed that surface, if you like, pre-cut, numbered, and then installed on site with quite a few adjustments. Actually, Ventura told me that, yeah, it's great to have the equations, but you still need to cut the bits considerably on site, which is also what Deep 5 students experience every day when they make models. There's a lot of basically tinkering with the results of the formula. So this is a detail of that element. So using the steel member, you just form the element along its length. The steel members were actually designed and drawn by AKT and then fastened to the edge member, following the discontinuity that I explained. This is basically a flight. Okay, it's oblique, 9 meters, and then it's broken by 1.5 meter worth of landing, so that a wheelchair can actually pose. That kink we've carried over throughout the structure. I had this really interesting discussion with Carlos Kucharik, the journalist who wrote the profile of the project in Riba Journal last month, and he asked me about that kink, and we both agreed that this wouldn't have passed muster in basically, as he called it, a high-tech office 20 years ago, when that particular sort of kink would have been perceived as a mistake. But nowadays, if you just let that peculiar logic of the movement, somehow, of the wheelchair carry through the entire steelwork, it actually looks quite contemporary, I think, although on the other side it looks a bit messy, but that's what you get for being literal. So this is a detail of that. The way it's done is that obviously once you fasten those to the edge member, you panel bit by bit until you basically get this quite extraordinary tapestry, and you can see the kink that I'm so fond of, somehow colonizing the entire geometry. All these elements are sheared, as I said. Everything in plan is sheared, oblique in space, then undulating, so that kind of instability in the end produces a rather sort of composite sort of surface. That's from the back. This is also how you clad the arrival. This is a bit that is a little bit like what we have at the office, what you see over there. Gradually somehow filling the space in front. The detailing I thought was quite beautiful. I mean, they did an amazing job trimming somehow the timber around the elements. This is something that you would have done with solid modeling, and then it's very nicely done also materially. What I like about those pictures, which I didn't take, these ones, is that there is someone in the contractor's team that has the same pathology somehow, someone really keen on what they do, very interested in photographing details, proud probably of the handiwork, and just going around and photographing it without being asked. And I thought this was really amazing. These are the people really that make the project, the ones that actually, make it really and ensure its success. This picture I took after a tropical storm, and shows you how the sort of gradual weathering of the form produces this incredibly vivid tapestry. And at the moment I'm in discussions with a contractor to try to find the right chemical to make this effect permanent. So it's pressure treated. The idea is that you would try to sort of keep that. It's quite beautiful because suddenly everything becomes very reflective. It's like a sort of mirror following everywhere, and it lasts a few seconds. I mean, within a minute and a half, it's basically all gone. It's dry. The timber surface, as I said at the beginning, is much more like this. It's just a series of discontinuities. This is the tall wave. That's where you sit. All this element is completely doubly curved. So that's the skeleton behind it, and this is the line when the double curvature meets the horizontal plane of the seating. So in order to get this built, the contractor developed a method which would allow them to use these as guides to tuck, the custom cut elements side by side along those guides without any kind of apparent joint. So with a reverse fixing system that guarantees this incredible smoothness, if you like, on the front side. They did this by creating this detail in which, this is the fin of, the curved forgot the technical term. It's kind of a back strip, steel back strip, which actually literally chops through the wood, which has these dowels, and on the back, the timber is actually, you can barely see it, it's actually scored. So the dowel can be simply inset into the scoring and then filled with epoxy. So you can actually push those elements on site into the right position. So you see this is a doubly curved area. You see the dowels are waiting. You just apply the element and then fill it with epoxy from the back and then let it dry. And it's incredibly dense, obviously, because it's, these are, this is only 500 mil span and they're all sort of holding each other. It's an element in the making. And this is the final shot. I got this one yesterday. I mean, this is really what it looks like, this week. It's already weathered more. You can see it. But everything is absolutely smooth and painless. That's a view of the, looking the other side. So there are some horrors, last minute adjustments of the railing and things, but this is inevitable. Let's say on the whole, the project was safe from any kind of strange decision. I mean, I think everybody somehow saw things with the same mindset.
I think part of the key to the success was really the control, and we've talked a lot about geometry, models, generation of form, but that was really from a global scale right down to the detail, and that's really where the responsibility comes from in developing forms like this, taking it right through to the nth degree. To have left this to the contractor alone to develop would, of course, been incredibly complex, very risky, and almost certainly wouldn't have achieved this sort of desirable result. So it's a rigor that needs to translate all the way through the project, from a global to a micro scale, really.
So we're going to finish with the quickly with the timber of the span 3, the big one, which again is always a problem. You always have to look at it independently. You see, as soon as it was hoisted in place, the basically cladding began. You had to to build scaffoldings inside it. As I said, this is as tall as a 2-story building, and quickly creating the largest timber expanse that this project has seen, starting with the floor, which again was made with prefabricated boards that were in fact cut on site for sort of last-minute adjustments, all the way to the doubly curved vit, which was again put together in the same way, painstakingly, bit by bit, by a crew of Chinese carpenters coming from actually the center of China. They don't even speak Mandarin. The contractor was talking to them in a dialect. So they're incredibly craft people with from a certain tradition that you can only really find in one region. You can see the scale and the joints while it was actually being finished, tapered by hand. Just in case you complain about the next Deep 5 model, I mean, each one of those pieces was actually cut by hand, which could have been done algorithmically, but obviously, that wouldn't have been cost effective, or even perhaps, as beautiful. So towards the end, you can see that the backrest meets the seating as smoothly as it does on all the other waves. And gradually the railing is sort of moving in, colonizing the corners to sort of block access, if you like, to those dodgy corners in which you could somehow, from which you could, let's say, climb onto the structure and possibly fall. And that's what it looks today. I mean, I got this picture yesterday. I mean, I'm going to talk a little bit about this. I was unhappy about the color for obvious reasons. You can see the difference between the original mesh color, which blends almost camouflage style with the rest, and this one, which looks like a curtain that's been sort of pulled like a veil, on top of the corner. But the handiwork, again, of the timber, I think is quite magnificent now that it's complete. Yes, I spoke about this. This was a bad idea. Every project has its own share. What I really wanted was to maintain the, instead of that sort of white coating for this detail, I wanted to maintain the rusty quality of the original, which have shown the rhythm of the steel balustrades much better, and the anodized, basically steel handrail. But in the end, issues of cost prevailed, and that's what we have today, which you have to live with, which I guess is okay, but I find it intrusive, if you like, in the scheme of things. Finally, views of the springing point. The landing, right where it crosses that path that I described earlier. The view that I really do not like, the one that will be used to publicize the project, it's the blob shot. It makes the project look quite vulgar, I think. It's inevitable. We drew it on the competition panels as well. I much prefer the intelligence of the other side, which shows this kind of negotiation between the sort of kinky deck and the purity of the periodic form, which of course here looks, much more spatial in the sense that the periodicity is now combining with the, if you like, the double periodicity creates this pinching, which, to say something about the structure in the end, you see the mid-height member that Paul added to the structure, which is right there, has this beautiful feeling of a bone that actually comes in and out of the elbow, you see? And you can see that by daytime as well as by nighttime. I think this is probably one of the most successful features of the project, which came out of that argument you made about somehow relieving the spine from the influence of those. And in the end, without it, I think that view would have looked even worse. So it's actually something that that's probably called experience as well for me. This is what Carlos and I were discussing, the fact that this looks faulty, when in reality it's actually simply expressing the alternation of flights and landings. The downside wave, which is, I think, quite beautiful on the landing end, right, basically where the bridge arrives. Oh, and the beautiful mid-height member now seen from the inside, which I think is an unbelievable piece of structure. The shot that I took last month with a worker adding the finishing touches to the paint, who was very happy to be caught on camera and posed for me briefly. Originally, Lawrence and I had wanted to bring people down there. I mean, it's quite obvious if you just look at this that in fact you can actually step on the flanges and come down. It's smoother than a stair. So we had envisioned that you would actually occupy the upside and the downside pods with a railing over here, but the client thought it was simply too much. And basically this now stays unused, if you like, unless you visit the underside of the bridge. I don't have a lot of night views. The concept of the lighting was to express the surface form. So blast light on that, basically on the inner side of the pods. You can see again the mid-height member now in, as we say, contre-jour in French, which is against the light. And wash the deck on the other side with those basically lights that are included in the railing. So the combination is this rather happy, sort of a, let's say, emphasis on the surface form, which in the end I think is a little perhaps too pronounced, but we didn't really have a say into this scheme. You see, that's what it looks like from the road. You know, it's fairly merry at all times of the year. It's also obviously for safety reasons, the light levels need to be quite high. It's already quite romantic if you visit, but it has to somehow be a bit brighter than the average. So you see the lights are actually tucked behind the backrest, and then they flash up all the way to the, almost basically to the arch itself. I mean, the halo should come a bit higher, but there was an issue with the wattage, which produces this kind of very strong effect. I much like this concept in which the LEDs were simply hidden into the railing and are washing basically the light onto the timber surface. I would have liked to actually do the same on that side, but the light levels of these were too low, if you like, as a concept to generalize for the whole project. Well, I guess that's it, really. We'll be going to Singapore next week for the opening, and you know, thank you very much for coming. And if you have any questions, Paul and I will be more than happy to take them.
Thank you.
Thank you.
George.
2 points really. One was about the issue of the actual pier itself that supports it and the problems that you had actually resolving that and actually ending up with just a pure rectangular pier rather than the more complex one that you designed, which I must admit the first time I saw it I actually thought was really quite beautiful. So that to me seems like a compromise. But also this idea where you said, this idea of the blob, where you're saying, you know, this is the most unsatisfactory shot for me. You mentioned about the pier, that it was the one thing you had a problem with because you had to design it. And it's the conversation I had with you about this idea of how far can numbers take you before you actually have to formally appropriate it and take on the consequences of the numbers. I mean, had you known about that blob shot, would you have changed your notation in order to resolve that? Because obviously it's not resolved for you now.
I mean, not really, in the sense that if you like, the blob shot, I think is a half surprise in the sense that you know, we looked at the 3D model. In fact, even the centerline model that Paul and I worked from, you know, the first days had that. It's just that, you know, we even included it on the competition panel. It is clearly the most impressive, let's say, the most formal corner. I'm not quite sure why, at least at IJP, we're not really coming to terms with it, in the sense that I find that it is too formal in some sense. In other words, the subtlety of the effects that you can show and discuss when you look at the timber work on the other side is a little bit lost when you simply look at, that pinching kind of element. So I couldn't have changed anything unless, of course, we changed the entire concept. Perhaps I'm a bit surprised that, for instance, when the client publicizes the project, they will only show that shot. They're also building a platform aside the one we already have, so that people can actually get photograph on axis with that backside. So it's becoming, if you like, the landmark view, which, I'm obviously, basically, I find interesting. But I suppose, no, you couldn't have really changed anything. And as for the pillars, the question you asked, yes, I mean, you're right. That's, that slideshow that we didn't really look at while you were preparing that write-up is in some ways almost ironic, where I would like to flash 25 solutions to show that when you are not designing with equations, you are cursed somehow with the need to make a decision, a design decision. You can have 25 solutions, and which one's good and wise then becomes a very somehow difficult answer. And some of the work that we do in the unit is trying to take on that question as well. If you had been part of the somehow of the formula, I would have had an alibi for accepting, if you like, either its beauty or some of its downside or shortcomings.
I think some of the studies were done with a formula when we were trying to resolve this idea with the pylon, but it kind of detracted then from the deck, from the main span of the bridge. The bridge seemed to lose some of the beauty that it had, some of the kind of simplicity in the form, and it then dragged this complexity down into the pylon, which, certainly from our point of view, we thought was beginning to confuse things, and I think that was the result of it. So, although there was two different perhaps approaches, one an analytical one a sort of an instinctive one, there needs to be an understanding that sometimes there needs to be that divide, I think, to bring these two types of forms together.
On the other hand, I mean, one is really trying also to imagine what that picture would have looked if we had gone for the kind of tree-like pier. I mean, it's obvious that there's something both appropriate and perhaps a little, I don't know, too literal somehow if the tree-like design had prevailed, which, I agree with you, is very beautiful, but is in somehow, yes, in direct competition with the kind of the pliancy and the presence of the deck itself. So I'd say that these pylons, which look unwieldy when they're stumps towards the end conditions, if you like, of the bridge, look very satisfactory when somehow the odd proportion takes over, because this is only 75 centimeters by 4 meters and is almost 40 meters tall. So even as a pylon, somehow it is actually quite excessive in a way that maybe the tree wasn't, but this is somehow in a more subtle way. Yeah, that's it's a paradise for skateboarding. Early on, we drew a various sort of series of obstacles. So we had to design charrettes, how many ways you can actually stop the skateboarders. The conclusion was that anything that you could put in the pathway would actually be dangerous. So the idea of introducing physical obstacles was abandoned, and instead we're relying on the goodwill of basically the kind of Singapore ethos, which means that if you put a sign like the one I showed earlier that says "Don't skateboard," people tend to stick to it, and even though they will go there and probably carve hearts on the timber and stuff, they will probably not skateboard, or at least I like to think so. I mean, it is indeed quite hard to look at this and not imagine that you could be we've even beveled the seating so that you can actually, I don't know what the technical term is, but sort of jump sidewise back and forth, and then you even have a little springboard. But you see, that should do it. I mean, one of the things that strikes you when you visit, and if you are ever in the region, I mean, obviously, what else would the architect say? But do visit the building. It's quite amazing in the sense that no amount of familiarity with the plans or the drawings, even for someone, you know, like Paul and myself, who've been looking at it for 4 years, no amount of that prepares you for the reality of it. And the main thing being that it's unbelievably steep. I mean, even at that prescribed slope, and despite all the mathematical adjustments, it is unbelievably steep, and you can imagine the velocity that you could acquire, you know, if you actually were skateboarding or using any kind of sort of cycling or sort of motion kind of device. Yeah. Yes, Gary.
It seems to me a bit a difficult decision how you determine how to add the timber parts, and it could go much higher or lower on both sides, and I wonder how you determine in a cross section.
So you're talking about this line?
Yes, and the other.
And this one?
Yeah.
Yeah, it's basically just, this one is 120, which is ordinary sort of railing guideline. So this is 120, and the actual anodized railing is a bit lower, and there's 2 of them. You can see them on some of the slides, one for handicap, one for basically regular users. So that's code. This one is a little bit different. This, as I explained early on, is also part of the equation. So in other words, the parametric study of that detail would have allowed you to go much higher when you look at that inner surface, which, you know, runs right above that. And that was simply a decision based on the idea that you want a backrest that is somehow at eye level, whatever that means, since the whole thing is sloping and turning at the same time, is not too high in order to make the pod enclosed, and is not too low that it would somehow look like an uneven railing, because if this was too close to the ground, you see your relationship. Say if you stepped on that sort of seating, then you would be above somehow the timber. So it's a little bit difficult to predict. Even today, you see, we've had to do all sorts of strange things in the pods to simply prevent people from, say, stepping on this and being above the timber line. But you see, the timber line somehow varies depending on whether you're actually standing here or there. So I'd say that this end somehow is a compromise between all those issues, the idea being that you don't really want to go so high that you would be somehow covered.
That's saying that you don't want to enclose, but you don't want people to see out, so you want them to be enclosed.
Yeah, there was a little bit of that compromise, yeah. I mean, if you think of it, in one of the competition drawings, we showed that going all the way up and providing shelter. So it's not like this wasn't an option. I mean, all you need to do is basically simply, you know, use that line. But in the end, I felt that it was better to treat this as a kind of variable, you say that, I'm sorry, not a backrest, but a variable, datum, let's say more like a railing of sorts, which is variable, rather than something that would be sort of body size and then be more like a sort of cover.
What does the datum do? I mean, what's the point of having it? I'm just curious how the theory behind it, how do you decide?
For this area, well, what it does certainly is hide that main structural element. Also, if people do sit here, you see at the moment, and if they stand, this is about waist size. If they sit here, this is almost eye level, and if they start climbing on this element, this becomes lower and lower until, if like, it no longer affords you protection. So in many ways, it was thought in such a way that it would maximize actually the railing sort of thing. In other words, it would maximize protection, while reaching a point where, you know, because it dwindles away, you have to intervene and either block this corner, which is what we did in the end, or use, you know, the steel railing, which is running this way and goes in that sense. So imagine it as a kind of variable railing that doesn't really do its job and that needs to be constantly compounded by additional kind of help. I mean, if you look at the final drawings, I think that's the final shot. Sorry, that's quite manifest. Yeah. You see, you can see it on this slide. This up to this point, this is still somehow waist size. By the time you get here, it no longer is. I mean, it's obvious. So you have to block this. I mean, the disadvantage of working with a doubly curved surface that undulates and swerves is that you can't rely on any kind of datum. On this side, it works because that's single curvature, and you can have a homogeneous railing. On the other side, you just have to negotiate that constantly. And I would like to point out that none of the 6 pods has the same seating arrangement. The mathematics is all different. They look the same, but they're constantly cut differently. They end differently. For instance, in this case, you see the seating goes all the way to the end and is lost because it's fenced off. On another pod, the seating might end here, and the oblique part of the ramp will just colonize the corner and so forth. So everything is absolutely custom. And therefore, maybe I can't answer in one way somehow. Or can't provide one answer, if you like, to the rightful question you're asking. Yeah.
What is your preferred state of the bridge, before the timber was put on it or afterwards?
Well, for me as an engineer, it's clearly the skeleton that I think is the interesting part. It's not to say I dislike the timber, but we look at buildings pretty much when they're finished, and very rarely do we see the structure. And I think a lot of engineers, that's what they like to be able to view. So the interesting thing about bridges is, of course, you get to see that. You get to see and you can detect how the thing is actually working. You can still see a lot of the structure from below, and a lot of that is exposed, and I think that's the kind of nice part about the design, really, that though it's got the surface there, it's still very, very apparent about what the bridge is doing and the geometry of it. So I think even in the end condition, for a structural engineer, it's fine.
I would answer the same. I mean, obviously I really enjoy the timber work, but these skeletal moments, which I cut on camera at different times, are, I think, superior in the sense that, I mean, I know obviously the project. This line here is a line of intersection between geometries. Everything was actually built. In other words, you have to imagine the secondary structure of this steelwork somehow embodying all those lines that were implicit in the design, and building them in such a way that they have grooves and can accommodate timber. It's an incredible kind of blueprint, if you like, of that immateriality. And then, of course, when it's covered, it becomes smooth and everything is lost. So I would also vote for this moment, which I understand is quite common. I mean, most architects, when you ask them, basically they do prefer the building site, I think, moment to the final product. It's often the case. There's something about that fleeting moment. It's like watching a baby grow. I mean, it's gone the next day, and there's something absolutely fascinating about that moment. Yes?
Both of you prefer the skeleton. Did you consider having part of the ribbon exposed, or using glass as on the side and on the deck?
Well, no. I mean, the short answer for me is no. We didn't really consider that. But the truth is, if you look at it from the back, in other words, the outer views obviously restore the primacy of the structure. From the outside, as you can see, the entire thing looks like the structure is somehow hugging the timber. Yeah, you can see it. Sorry. Which one? Yeah, you can see the structure somehow, all of it, because again, there are no hidden parts in this design. I mean, it's the difference between infrastructure and building. There is no interiority. There's no front and back. So everything here is absolutely visible, and yes, you see that perhaps some of that, is still visible. The other nice thing that you can see on that shot, and that will be my sort of last comment, is this idea that they are parallel, and you see the parallelism of these elements combined with those shifts produces something that looks like maybe a distortion of the lens when you look at the kind of edges of a photograph, which is focused on the center and then somehow falls apart. But it's not. This is a very narrow angle, and yet these distortions are actually purely spatial. So subtle things that in the end make the project, I think.
You must be really unhappy with the cross-bracing.
Yes, yes. You had to for the larger spans towards the middle. Yeah. I mean, there's a couple of things that were done by obviously the closing stage.